அனைவருக்கும் வணக்கம். Hello everyone. In this video lecture, I want to discuss the significance of minimization of Gibbs free energy in chemical reaction equilibria with a simple example. From the basics of chemical engineering thermodynamics, we know that for any spontaneous process, del G at constant temperature pressure should be less than or equal to 0 for all the spontaneous process. Also, we know that del G at constant temperature and pressure, that is equal to del H minus T del S. If you want to minimize G, del H should be decrease and del S should increase. That's why del G represent trade-off between decrease in energy of the system and increase in the entropy of the system. I have taken a simple example, that is a reaction between hydrogen and chlorine to give 2HCl. I assume it is ideal gas at a low pressure. The bond dissociation energy of each component is given as 4.5 electron volt for hydrogen, 2.5 electron volt for chlorine and 4.5 for HCl. Let me write this stoichiometry for dissociation. 2 hydrogen dissociate to give 2H plus, 2 chlorine dissociate to give 2 chlorine, 2 HCl dissociate to give 2 hydrogen plus 2 Cl. In order to get the stoichiometry from this, we need to add these two things, that is 4.5 plus 2.5 minus 2 times of 4.5. We will get 2 electron volt. That is, for this reaction to progress, 2 electron volt energy is decreased. It means that the reaction is favored by decrease in the enthalpy of the reaction. But if we consider in that way, we may expect 100% conversion of hydrogen and chlorine to give HCl. It means that we have 100% pure HCl. It is not so, because Gibbs free energy also controlled by increase in the entropy of the system. If we have complete conversion, we have only pure HCl. But if you have partially reacted mixture, we have hydrogen, HCl and chlorine. That means that we have possibility of more randomness in this case than this case. Therefore, in this case, the randomness is more than this case. Therefore, G, that is Gibbs free energy, represent trade-off between decrease in the energy of the system and increase in the entropy of the system. Let me take simple example to illustrate this one. Let me take a same reaction. Hydrogen react with chlorine to give 2HCl. Let me take N1, that is equal to number of moles of hydrogen, N2 that is equal to number of moles of chlorine, N3 number of moles of HCl at time equal to T, whatever time it may be. Initially I have taken N1 naught 1, N2 naught 1, N3 naught as 0 when time equal to 0. Let me define the term called extent of reaction. Therefore, after some time N1 will be 1, since I have taken 1 moles of hydrogen at starting, minus epsilon. According to stoichiometry, whenever 1 moles of hydrogen react, 1 moles of chlorine is reacted. Therefore, N2 also same, 1 minus epsilon. By looking at the stoichiometry, whenever 1 moles of hydrogen reacted, we have 2 moles of HCl. Therefore, N3 will be 2 epsilon. Now I have defined N1, N2, N3 in terms of epsilon. Now let me determine Gibbs free energy of the system. Gibbs free energy of the system, that is summation of Ni Gi bar, that is partial Gibbs free energy. For our system we have three species, therefore I can expand this N1 mu1, since partial Gibbs free energy is nothing but chemical potential, plus N2 mu2 plus N3 mu3. From the basic definition of chemical potential in terms of standard Gibbs free energy, we know that mu I, that is equal to Gi naught plus RT ln Fi bar divided by Fi naught. Since we assume it is ideal gas, Fi bar can be written as PI, that is partial pressure of ith component, and Fi naught is nothing but pressure at which system behave like ideal gas. Most cases at 1 bar system behave like ideal gas, therefore I can take Fi naught as 1 bar. Therefore I can rearrange this equation: Gi naught plus RT ln partial pressure of ith component divided by 1 bar, it is equal to mu I. Let me write the Gibbs free energy of the system from the equation here. I have written here. Let me simplify this equation further. That is equal to mu I Gi naught plus RT ln Pi plus RT ln P. Let me subtract RT ln P. Therefore, we get Gi naught plus RT ln Pi divided by P. This term and this term are combined, plus RT ln P. This is nothing but Yi. It is Yi, that is equal to partial pressure of ith component divided by total pressure. Therefore, mu I is equal to Gi plus RT ln Yi plus RT ln P. Let me write the Gibbs free energy of system. G, that is equal to N1 mu1 plus N2 mu2 plus N3 mu3. From this, let me substitute the terms for mu1, mu2 and mu3. Right? That is G naught N1 G1 naught plus N2 G2 naught plus N3 G3 naught plus N1 plus N2 plus N3 RT ln P. For this term I have written here, plus for this term let me write N1 RT ln Y1 plus N2 RT ln Y2 plus N3 RT ln Y3. Now let me replace N1, N2, N3 R in terms of extent of reaction. That we know that N1 is equal to 1 minus epsilon, N2 that is equal to 1 minus epsilon, N3 that is equal to 2 times of epsilon. Therefore, we get G that is equal to, so here N1, N2 that is equal to 1 minus epsilon. Therefore, I can take, that is a common term, 1 minus epsilon into G1 naught plus G2 naught plus N3 is nothing but 2 epsilon to G3 naught plus, what is N1? It is 1 minus epsilon, N2 is minus 1 minus epsilon, N3 is nothing but 2 epsilon. Therefore, minus 2 epsilon and plus 2 epsilon we cancel out. I have 2, therefore I will write 2 RT ln P plus, in this term we have N1 1 minus epsilon RT Y1 plus 1 minus epsilon for this term RT Y2 plus entry is nothing but 2 epsilon RT ln Y3. If you look at this equation, this first term, let me tell you, this is the first term. It is merely constant. This term is constant. Since total pressure is a constant, we no need to bother about that. This term, that is term as, let me term as 1. This is the nothing but Gibbs free energy of pure components. G1 naught is nothing but Gibbs free energy of pure component 1. G2 naught is nothing but Gibbs free energy of the pure component 2. And G3 naught is nothing but Gibbs free energy of component number 3. And this term, that is this term, accounts for entropy change of the ideal gas mixing. Let me write, it is del G of this del G of ideal gas mixing. Let me plot this equation graph. G in y-axis and this complete this extent of reaction in the y-axis. I have shown here. This is something but first term, that is, as I told, that is something but 1 minus epsilon into G1 naught plus G2 naught plus 2 epsilon G3 naught. That is Gibbs free energy of pure component. At starting we have only epsilon. Here if you look at here epsilon equal to 0, that means we have only hydrogen and chlorine. At this level, that is epsilon equal to 1, where we have pure HCl, that is maximum level, and this term is adding other term to this term. This difference is nothing but del G of ideal mix. And if you look at here, if we have started with the pure hydrogen and chlorine, the Gibbs free energy decreases. Look at this term definitely will decrease, since at starting it is 1, so G1 and G2 will be there. As extent of reaction going to increase, this term going to decrease. Therefore, there is a gradual decrease here till epsilon equal to 1, where we have only this term. So here, from here to here, it is decreasing for pure component. And addition to that, we need to add other terms. These two terms, we don't need to worry about this term since it is a merely constant. And here also, as epsilon decrease, this value going to decrease, this value going to decrease, but this value going to increase. But thus we have decrease in Gibbs free energy till a minimum value of Gibbs free energy. Suppose if I am going to start with the pure HCl, even though enthalpy going to increase, entropy also going to increase. Therefore, Gibbs free energy decrease in this manner till it reaches a minimum value of Gibbs free energy. That is what it is called, a minimization of Gibbs free energy. This point is called as equilibrium point, or at this point we are calling as equilibrium conversion. So whatever principle we applied in the phase equilibria can be applied as minimization of Gibbs free energy in chemical reaction equilibrium. Thank you for watching the video.